Good evening, everyone. This is a summary session of the course Geotechnical Engineering (NPTEL), and this is the last class. This is the last live session. So this session is going to be of only 1 hour, and since nobody has joined, I'm going to start this session, and I'm going to just give a quick recap of all the major chapters and contents which I have mentioned, which I have taught in these live sessions, including the, the theoretical part and some tricky questions which were there in the previous live sessions. So, I'm going to start this summary session right now. Basically, the first chapter of this geotechnical engineering was on the origin of soils and rocks, followed by the index properties of soils, the basic relationships between weight ratio, porosity, unit weights, all types of unit weights, then came the soil classification system, soil structure, and then there was action, permeability, flow of water through the soils, hydraulics, and then there was consolidation, there was pressure, that is uh, static pressure on the soil. How can you derive that static pressure using Bose theory, Marx theory? Those chapters mainly had the numericals, the numerical part. So I have not incorporated any question from those chapters which were specifically filled with numericals. I have just incorporated some questions, some MCQs, which are basically conceptual and which will help in understanding the main concept of any particular topic in that particular chapter at a glance. So here there are 15 questions which are basically the same questions which have been mentioned in the last 12 live sessions. Some have been skipped because, as I've said, they were purely numericals. So basically, this geotechnical engineering, it consists of the basic concepts of soil mechanics and not the foundation engineering part. It is engineering. It is in part two of this same subject. So in this chapter, in this unit of in this course of geotechnical engineering, only the basic fundamentals of soil mechanics, as I've mentioned previously: soil structure, soil classification, index properties, uh, compaction, consolidation, permeability, then seepage, stress calculations, soil settlement. These are the basic things or the basic concepts which are present in this particular course. So right now, as I've been saying, I will just revise the entire session of geotechnical engineering in the form of some MCQs, and that this video will be also be uploaded on my YouTube channel for anyone else to see what what I have taught in this summary session. So let's start. The first question which I had given from the week one is, which of the following type of soil remain at the place of formation? Now, as we all know that soil is formed by weathering of rocks and then is transported from one place to the other. But some soils, they are not transported; they are deposited at their place, at the place where the rocks have been weathered. So, which of the following type of soil remain at their place of formation? Means after the weathering of rocks, these kind of soils, they remain at their place of formation. The options were aeolian soil, marine soil, residual soil, and colluvial soil. So as the name suggests, the answer will be residual soil because they reside, they stay at their place of formation. But we should know what the other three options mean. What is the meaning of eolian soil? What is the meaning of marine soil? What is the meaning of colluvial soil? So aeolian soil basically are those soil which are transported by the wind. Marine soil, as the name suggests, are transported by the sea water, and colluvial soil are transported by the action of gravity. So this question, the answer is residual soil remain at their place of formation. Yes. So residual soil remain at their place of formation. Next question: what is degree of saturation? As we have seen in the throughout our live sessions, the degree of saturation which is being noted by S, it is very important. It is very important to calculate many other parameters, specifically the void ratio. Void ratio equal to Wg by S. So this relationship goes Se equals to Wg, where E is the void ratio, W is the moisture content, and G is the specific gravity of soil solids. So this degree of saturation is very important to find out the void ratio. Now, what is the degree of saturation? This is the basic definition. The options were moisture content of soil mass in its natural state, ratio of volume of water in a soil mass to the volume of soil solids, ratio of the volume of water in soil mass to the total volume of voids in it, moisture content of soil mass in its saturated state. The answer will be the third option, ratio of volume of water in a soil mass to the total volume of the voids in it. That is, volume of water if it is VW, and volume of void it is VV. How much space the water can occupy given that the volume of void is VV. This when expressed as percentage will give us the degree of saturation. So it is the ratio of the volume of water in the soil mass to the total volume of voids in the soil. Next question: the maximum water content at which I guess I have to confirm that I still recall. Since there is no one in the call, I'll just do one thing. I'll just put my window as a PowerPoint because there is no one in the call. So there's no point in showing the Google Meet. If anyone joins in the call, I will just shift to the Google Meet screen. The maximum water content at which a reduction in the soil in water content will not cause a decrease in the volume of soil. This is a very important question. The maximum water content at which a reduction in water content will not cause a decrease in soil mass. When we are decreasing the amount of moisture in the soil mass, gradually the volume of soil mass also decreases. Now, at which point, that is, at which moisture content, it is such that after we decrease the moisture content after that particular point, the volume will be constant. Volume will not decrease. Okay, so here we can see this particular graph as usually shown over here, taken from, I guess, any standard book will have this graph. It is moisture content on the x-axis and the volume of soil mass on the y-axis. Now it is showing the consistency limits. What are the consistency limits? Liquid limit, plastic limit, and shrinkage limit. This is the liquid limit and the last WL, after which the soil goes into a goes into completely into a liquid state. Now before that, it is the plastic limit. What is that? The soil can be deformed. Between WP and WL is the plastic state. The soil can be heavily deformed. After that comes the semi-solid state, where the soil is kind of stiff. It will be there will be difficulty in deforming the soil. So as we are moving in the graph from the right to the left, we can see that we are gradually decreasing the moisture content, with which the volume is first decreasing up to a certain point B, after which the volume is constant. Now this point B, this is called the shrinkage limit. This is called the shrinkage limit. The soil, it stops shrinking after this point, and it has a constant volume throughout, even if the moisture content is being reduced to zero. So the answer of this question will be the maximum water content, which reduction in water content will not cause a decrease in the volume of soil mass. The answer will be shrinkage limit. Okay. Next question. Now flow index is, what is flow index? If we have learned the liquid limit test using the Casagrande apparatus, where we need to place a soil with a certain amount of moisture content in that Casagrande apparatus, the that container, we need to cut a groove with that standard tool, and then we need to give certain number of blows in that particular container, that in the particular machine, using either mechanically or manually we can do that, such that the groove which we have done, it closes. Now that number of blows will be then plotted in this particular graph, number of blows in logarithmic terms with the moisture content. Now from this graph we can find out the liquid limit of the particular soil, which is the moisture content corresponding to 25 number of blows. 25 number of blows. Now this is called the flow curve, where we have moisture content on the y-axis versus number of blows in logarithmic scale on the x-axis. This is called the flow curve, and slope of this curve, del y by del x, slope of this curve will give us the flow index. The options were measure of particle flow after complete saturation, degree of stiffness after reduction in moisture content, slope of the flow curve in liquid limit test, difference between liquid limit and plastic limit. So the answer is clear now. The answer will be slope of the flow curve in liquid limit test. Flow index is the slope of the flow curve. The formula for this is flow index IF equals to del y. What is del y? Del y is difference in the moisture content. W2, suppose final minus initial, W1 divided by, it is decreasing, so it will be log minus 10 N1 2. If W2 is this one, if W2 is in the upper hand of the y-axis, W1 is in the lower hand of the y-axis, then corresponding to W2 will get N2, that is less, and corresponding to W1 will get N1, that is more. So it is 10 M1 by N2. A soil has liquid limit of 20% and plastic limit of 14%. As per IS classification, the soil is. The options were inorganic cells with high plasticity, organic clays of medium to high plasticity, inorganic clays and silts of low plasticity, inorganic clays of medium plasticity. So this question is to be solved using the plasticity chart as per the Indian Standard Soil Classification System, which has plasticity index on the y-axis and liquid limit on the x-axis. Now, this line is called the A line, and the equation for the A line is IP equal to 0.73 WL minus 20. Above this A line, we have soils of we have soil. We have which kind of soil? We have inorganic soil, and below this A line, we have organic soil. Now, again, there are two partitions at liquid limit of 35 and 50. Below 35, we have soils of low plasticity. Between this two range, we have intermediate plasticity, and above 50, we have high plasticity. And there is a thin range over here, the shaded portion that we can see CL-ML between 4 and 7 of plasticity index. It has clay and silt of low plasticity, and both will be inorganic since it is above the A line. Now what we have over here, we have liquid limit of 20% and plasticity of 14%. So we can find out the plasticity index IP, that will be equal to liquid limit 20 minus 14. That is equal to 6. So plasticity index is 6. So we know liquid limit is 20. So if we take 20 over here and then we go up, 6 will lie between 4 and 7. That means the soil is falling in this shaded portion, Cl-Ml. That means inorganic silts and clays of low plasticity. We have in the third option inorganic clays and silts of low plasticity. So this is the answer. Inorganic clays and silts of low plasticity. This chart is again a very important chart for solving these kind of problems, and the equation of the A line, it needs to be remembered because problems also come with respect to this equation, and the WL in this equation is the liquid limit, as I mentioned. Okay, so next question: which of the following is constant for a given soil? Bulk unit weight, unit weight of soil solids, dry unit weight, and saturated unit weight. Now, before giving the answer of this question, for this constant, we should know how to define each of these terms. Bulk unit weight, that is gamma, if I write T, bulk unit weight, that is equals to weight by volume, weight of the entire soil by volume of the entire soil. For soil solids, write gamma S. Obviously, solids means we are not considering water or air, so I will be writing over weight of the soil solids, or in other words, dry weight of soil divided by volume of only the soil solids. Dry unit weight, for that we need gamma D, which is equals to gamma D, which is equals to again weight of the dry soil but here dry unit weight means total volume of soil, gamma D by V, and saturated unit weight is what? It is gamma sat. It is the saturated weight, W sat, divided by the volume of the solids. As we can see in these four options, in the first, third, and fourth option, we have V as the denominator. We have V is the total volume of the soil as the denominator. But if we are concerned about the entire volume of soil which has water and air in it, then due to expulsion of air or water, the volume might change, and so this volume might not be constant for the given soil. And if V is not constant, then gamma will also be not constant. Gamma will also be changing. So I can say if V is not constant, if V is variable, then gamma T, that is the bulk unit weight, gamma D is the dry unit weight, and gamma sat, that is the saturated unit weight. These three are all variable. These are not constant. These will not be constant for a given soil because any moment air or water can get expelled out because of due to any force. So what is constant? Obviously, the volume of soil solids will be constant because when you are considering a given soil, a given mass of soil, there will be a fixed number of soil solids, and a fixed number of soil solids will have a fixed constant volume. So in this case, since this is constant, and obviously fixed number of solids will also have a fixed mass, this is also constant. Hence, gamma s will also be constant, and hence unit weight of soil solids is one property which is constant for a given soil, gamma s. And for this reason, to calculate the specific gravity of soil solids, we take the specific gravity of soil solids as a reference for solving any numericals or any laboratory test because of the consistency of gamma s. So the unit weight of solids is constant for a given soil. Next question. BIS, that is Bureau of Indian Standards soil classification, is based on grain size distribution, plasticity properties, both of the above, or none of these. Now, as I have mentioned in the previous sum, there was one chart. This, according to the IS soil classification system, this takes into consideration the plasticity properties. As you can see, plasticity index is there, liquidity limit is there. So the plasticity properties, as I mentioned before, has already been taken into consideration for this Indian system of classification. Now we go to the grain size distribution. Now, as per the grain size distribution, the Indian classification, they have strict boundaries for the grain size distribution, such that clay will have a maximum of 0.002 millimeter, silt will have a maximum of 0.075 millimeter, 75 microns, and then after that it starts the sands, fine grain, medium grain, coarse grain, then starts the gravels, then boulders. So yes, so grain size distribution is also taken into consideration while classifying the soil as per the Indian standard system. Hence, both of these properties are being used, grain size distribution and plastic properties. Because as I have mentioned, clay has a fixed size range, not size range. Silt has a fixed size range. Sand has a fixed size range, and gravel has a fixed size range. So less than 0.002 is less than 2 microns will be clay, 2 micron to 75 micron will be silt, from 75 micron to 4.75 millimeter will be sand, and beyond that it will be gravels and boulders. So plastic properties and grain size distribution, both of them take part in the Indian system of classification, and hence both of the above is the correct answer. Next question. For the same soil type, the effect of heavier compaction is true. Yes. So if we see optimum moisture content, that is W, this is the dry density gamma D. For one type of force effort, we get this kind of curve. If we give a heavier compactive effort, we get this kind of curve. What does it do? It decreases the optimum moisture content, and also it increases the maximum dye density. From this point it goes to this point, and the optimum moisture content comes to this point from initially this point. So the effect of heavier compaction is to decrease the optimum water content. Yes, this is right. Increase the maximum dye density. Yes, this is also right. The other two options were decrease the maximum dye density. No, it is wrong. And effective shear stress, it doesn't have any effect on shear stress directly, because we are only talking about the compaction results of this force. So the first and the last options are correct. Neutral pressure is. Now, what is neutral pressure? Neutral pressure is the pore pressure in the soil. The water in the pores, they also exert particular pressure such that total pressure equals to effective pressure plus neutral pressure. Total pressure equals to effective pressure plus neutral pressure. This effective pressure is defined as the grain to grain transfer of load throughout the soil mass. It does not consider the effect of pore pressure. When there is a capillary action in the soil, then the pore pressure becomes negative. If the pore pressure becomes negative, then according to this equation, we can say that total pressure after capillary action is equals to effective stress minus u under capillary action. So effective stress will then be increased plus C. Now this is important. Why? Because in this question I'm asking about the nature of neutral pressure. What is the nature of neutral pressure? So here total pressure, what am I doing? I am adding, in normal cases, I am adding the pore pressure with the effective stress. So I can say that if this is the water table and this is the soil layer and this is the water table, mark it like this. Then below the water table, if this is the line showing the pressure distribution, below water table the pressure will be compressive. This is the positive side, this is compressive, this is plus. Above the water table, the soil, due to capillary suction, it will be in tensile force, it will be in a tensile state, so that will be negative. So before, above the water table, if there is a capillary action in these places, in the capillary fringes, in this soil layer, in this soil zone, then the soil will be in tension and the pressure will be going like this. So I can say that neutral pressure is, the options were always tensile, no. Always compressive, also no. Compressive below water table and tensile above it, yes, because compressive below water table, it is positive below water table, because of which total pressure increases, and tensile above it, yes, because of which total pressure decreases. So compressive below water table and tensile above it. This is the right option, option number 3. And fourth option was just the opposite, compressive above and tensile below. This is wrong, because in the case of capillary fringe only, it is tensile. Next question. Seepage pressure is sorry, seepage pressure. Now when water is percolating through any particular soil, or in that case any fluid is percolating through any particular soil, that exerts a particular pressure to the soil grains, and when that particular water exerts a pressure, sometimes the pressure, if it is against the direction of the effective pressure, in that cases conditions like quicksands occurs. So, in the seepage analysis chapter, flow through soils chapter, we have learned that this question was there, and we have also learned that fluid flowing through or percolating through soil, it exerts a kind of pressure which is significant from geotechnical point of view, because what kind of structure we need to construct over a particular soil, if we do not know the behavior of water underneath the soil, then it will be difficult for us to come to a decision regarding the, the construction of the geotechnical structure. So in this question, the options of these questions are equal to pore pressure, impact pressure of precipitation on soil, pressure exerted by percolating water on soil, or none of these. So it is equal to pore pressure. No, pore pressure, it will not be equal to pore pressure, because pore pressure is the pressure of static water present in the voids of the soil mass. That is the pore pressure, static water pressure, which I have discussed in the previous question. This is pore pressure or neutral pressure. It is the same thing. Now in this question, so this is not the answer equal to pore pressure. Now impact pressure of precipitation on soil, obviously not, because when it rains, the impact of rainwater on soil is not called seepage pressure. Seepage is a particular phenomenon of behavior of water in soil. So it is obviously the third answer, pressure exerted by percolating water on the soil. So in these kind of cases, when the water is percolating in an upward direction and this pressure is going to be equal to the effective stress, in that case, as I mentioned previously, quicksand condition occurs. Quicksand condition occurs when the effective stress of the soil mass or the sand becomes equal to the upward seepage force. And in that case, it is common in sands, because sands do not have any cohesive force, any cohesion. The entire shear strength is governed by the normal stress or the effective stress of sand. If that becomes nullified, sand has nothing to hold itself on. So it is the pressure exerted by percolating water on the soil, seepage pressure. Seepage velocity is rate of discharge per unit cross section area of soil, rate of discharge per unit cross section area of voids, discharge velocity under constant head, and discharge velocity under variable head. Now we have two kinds of velocity we have learned in flow through soils. One is the discharge velocity, this V, and then the seepage velocity, Vs. Now these are related to each other using the porosity of soil. How? Porosity is obviously always less than 1. So Vs, Vs equals to V, discharge velocity, by N. N is the porosity. Since N is less than 1, Vs will be more than V. V or V is less than Vs. What is V? V is the discharge velocity. That is, when we go for the Darcy's equation, Darcy's law, Q equals to K I A, Ki equals to V. This is the discharge velocity. In discharge velocity, when we calculate the discharge velocity, we take into consideration the entire cross section area of the soil mass, which is wrong. Why? Because if we have a cross section of the soil mass like this, there will be soil particles like this. But when water is percolating through this particular cross section of the soil mass, then it is essentially moving through the pores or the opening in these places. So this entire cross section area is not taking part in seepage. The area of voids is taking part in seepage. And since the area becomes less, for the same discharge, we can get a greater magnitude of velocity. And that velocity is what we called as the seepage velocity, which we can find out by dividing the rate of the discharge with the cross-section area of voids. So Q by A, if it is equals to V, then Q is a discharge divided by the area of area of the voids will be giving us Vs. This has a derivation which can be found out in any standard textbook. I followed BC Punya, which is a very good book in making you understand the problems and concepts of soil mechanics. So, and this part is written very well in that book. So, seepage velocity is the rate of discharge per unit per section area of the voids. This is the second option is the correct answer. Now, the next question was contact pressure depends upon the elastic properties of. Now, this one I have discussed in the stress chapter, in which a footing was there. There was a footing, and there is a soil beneath it. Then there will be, first of all, there will be a settlement, and then there will be a pressure distribution that will be uniform or variable depending upon the type of footing and the type of soil. So in this case, contact pressure is also dependent on the type of footing and type of soil, because whether it is rigid footing or a flexible footing, whether it is a sandy soil, that is a granular soil, or a cohesive soil. In that fashion, the intensity of contact pressure, the uniformity of contact pressure, and the settlement will vary. So here we have said that contact pressure depends upon the elastic properties of soil only, footing only, both of this, none of this. So as I've said, it depends, the contact pressure depends upon the elastic properties of both the soil and footing. So both of this is the correct answer. And if there is any doubt regarding this, in that chapter of contact pressures, I have given four problems, separate problems of flexible and rigid footing and sand and clays, and shown in every problem the variation, the type of variation of the contact pressure and the settlement. So that video is there in the YouTube and also in the Google Drive. You can check and have a better, more vivid idea about this concept. So yes, contact pressure depends upon the elastic properties of both the soil and footing. Next question. Yes, this chapter consolidation I think is the most important chapter, because it has so many parameters, so many dimensions with it, including the settlement part. That I have given three questions from this consolidation chapter. These are all revision questions, but I want that this concept should be clear, very much clear to whoever is studying the basic concepts of consolidation in soil mechanics. So the first question with respect to consolidation was in partially saturated soil, the initial consolidation is due to. So in partially saturated soil, it has a three-phase condition. It has the soil solids, it has water, it has air. Now, when I say squeezing out of water from the voids, obviously consolidation means squeezing out of water from the voids. In the third option, we have expulsion of highly viscous water. That is also possible, it is also a part of consolidation. But here I am talking about specifically two things. The first part that needs to be checked is the initial consolidation. The second part that needs to be checked is partially saturated soils. In partially saturated soils, this kind of soils follow this three-phase system, obviously because it has air in the voids and water in the voids too. So in this case, during initial consolidation, what does it mean? It means the initial phases of load application. In consolidation, we apply a load and gradually the water seeps out. The initial phase, when the water is starting to seep out, in partially saturated soil, does the water seep out initially? The answer is no. It is because air is also present in the voids. So, on application of the load, initially, the first thing that will happen will be the air will come out of the voids and compress the soil mass. It is a kind of compaction, only that it is a static and a slow gradual load. The air will come out and then the soil will get compressed. After the air gets expelled, then the water will start squeezing out. So in the initial stage, in soils which are partially saturated, the air is first expelled out. Hence, the option 2 over here, expulsion and compression of air in the voids. This is the right option. I repeat once again, initial consolidation means the first stages of consolidation, and in the soils which are partially saturated, in those kind of soils, air is also present in the voids, due to which when we start applying the load, the air is the first thing that will come out of the void. After that, water is going to come out. So in soils which are partially saturated, the initial consolidation is due to expulsion and compression of air in the voids. I hope it was clear. This question is another conceptual question from the chapter of consolidation. Consolidation of soil is due to load which is static and short term, dynamic and short term, static and long term, dynamic and long term. Dynamic loads are not generally applied in case of testing and identification of soil parameters because it is difficult to control the dynamic loads in first place, and in certain specific laboratory conditions needs to be maintained for that. But in case of static loads, when we talk about static short-term loads, the first thing that comes to our mind is compaction. So this is one of the basic difference between compaction and consolidation. Compaction, if we say, and consolidation. In compaction, there is a load applied on the soil specifically and exclusively to drive out the water and reduce the volume. So that load is not only static, it's also a short-term load. And there are many instruments, rollers, dammers that are being used for compaction of the soil. Now in consolidation, it is a more gradual process and it has many other dimensions attached to it. We get to know many soil properties if we consider the process of consolidation in soil. For that, the load which is being applied in case of consolidation, the load is applied gradually. It is a long-term load. So, I can say over here that static and short-term load belongs to compaction and static and long-term load belong to consolidation. This is the first major difference between compaction and consolidation. I hope it's clear. So the answer of this question will be consolidation of soils is due to load, which is the option is static and long term. If the question was compaction, then the answer would have been static and short. I hope it was clear. Last question. Secondary consolidation is mainly due to the. Now, in this question, the previous question, I have mentioned about the initial consolidation phase, the initial phase of consolidation, and I have mentioned it for partially saturated soils. Generally, in nature, we will not find soil which is either fully dry or fully saturated. We will find soils which are partially saturated, which has air inside them. So yeah, this is the three-phase system. This is the soil solids, this is the water, and this is air. So we can divide the consolidation phase into three parts. First is the initial consolidation. Then comes primary consolidation. And then comes secondary consolidation. Now I have already discussed about the initial consolidation. What happens in initial consolidation? The air starts getting expelled out. The air starts getting expelled out and the soil gets compressed to a lesser volume. Comparatively to a lesser volume, the soil gets compressed in initial consolidation. Now what will happen after all the air in the soil has been expelled out? At that point of time, initial consolidation will end and primary consolidation will start. In this phase, that is phase 2, what will happen? Since the air has been expelled out, the water will start getting expelled out gradually, because it is the load, as I mentioned in the previous question, the load is static and long term. So gradually the water start getting expelled out. Water start getting released from the soil mass. Now what will happen when the water gets released? Now after a certain period of time, primary consolidation will obviously take more time than initial consolidation. After a certain point of time, when almost the entire water have been expelled from the soil mass, we can be never 100% sure that the soil is now completely dry or devoid of water. The soil particles may have with them attached to their surface highly viscous water, like this. And because of this highly viscous water which are present even after expelling out of water in the primary consolidation, because of this highly viscous water, the soil has a particular type of arrangement. It cannot come to a closer arrangement packing. Now in the case of secondary consolidation, that is on further application of load after the removal of water from the soil, that is, we think that water has been removed but still there is water in the form of viscous water. So in this secondary consolidation, what happens? These viscous water, they gets expelled out, and once they get expelled out, these particles will come closer and arrange themselves in a different manner. This arrangement is going to be permanent, because even if you remove the force, these particles will not come back to its original place because the water has already been expelled out. So this readjustment of these particles is plastic and not elastic. It is a permanent deformation or displacement of these soil particles on the expelling out of the viscous water between them. So to sum up, this secondary consolidation, it consists of what? It consists of first expulsion of the highly viscous water. Yes, this is true. And along with that, the soil particles, they start rearranging themselves permanently to get into a new arrangement. So it is a plastic readjustment of solid particles. Also true. So the answer of this question is both of the above. So in case of initial consolidation, only the air is moving out and water and soil is not getting affected. In case of primary consolidation, only water is getting out, soil is not affected. In case of secondary consolidation, in the case of secondary consolidation, highly viscous water moves out, also affecting the solid particles. Hence, we can see in this three-phase system, it is what is available naturally in this in the soils which are partially saturated. Have they have air, water, and soil particles, solid particles, all three. We can see that all the three phases, that is air, water, and soil, they take part in the consolidation processes, and all the three processes are significant to find out the to find out and to analyze the entire consolidation process of the soil mass. I hope this was clear, and I hope this session will be important. I have already recorded this session, and I believe all the other live sessions, the recorded videos are available on the YouTube channel. I'll be uploading this video also on the same channel. Thank you everyone. So this is the end of the live sessions. Thank you.